Hi guys, Utkarsh this side. Welcome to What I Learned in a Day, episode 3. So today I learned how to create URDF of my robot using ROS2. So in the last episode we imported these STL or mesh files to Linux for creation of our URDF. So first what we will do is create a workspace. So we will name our workspace as Mobi. So we'll name our bot as Mobi. So mkdir Mobi workspace. We have created a workspace. Then we will do callcon build. So here the workspace has been built successfully. Now these folders also appear: build, install and log. We'll create our ROS2 package named as Mobi description. So it will create the URDF, it will store the URDF of the robot. So we will do ROS2 pkg create ROS2 package create. Package name is Mobi description and build type is amint cmake. So it is a cmake package. So here our package has been created. If we see, Mobi description package has been created, and if we go inside the package Mobi description, we will see that we have cmakelist.txt, package.xml, include and src. So besides that, we will create few more files to folders to store the URDF. So first we will create a folder named as URDF, which will store the URDF files or XML files. So now if we see, we have these folders: launch, meshes, RViz and URDF. So now we will move to VS Code to write our URDF. So I'll go back. Now I'm in my workspace. Now I'll simply write code space dot. So it will open the VS Code. So if we'll click on URDF and we'll click here, we'll create a new file. We will name it as mobi.zacro.urdf. So it will be the main URDF file. Now what we will do is, so we had stored these STL or mesh files here. So we will do Control X and we will paste these mesh files in the meshes folder we just now created. So we will start by writing link. So we will simply like link. So it will directly give us the prompt. I'll press enter. So it gives the basic structure of the link. So the link name is base link. So this is the base link. Inertia, right now we are not concerned about it because this we will use when we were importing the bot in Gazebo. So in RViz, inertia is not of any concern. Now visual name, we don't want to give the visual a name. We will simply keep the tag as visual, and origin we will keep it as 0.0 only. You will see the way I imported, the bot will directly come at the place as it was shown in the Fusion 360. We just have to tweak the joints a bit. So geometry, instead of box, we will write the location of the mesh file. It is in the package, then Mobi description, then in the meshes, name of the mesh file is baselink.htl, and I have scaled it down so that it fits in RViz properly. And material name, so I've given the material name. Collision will be same as the collision of the visual tag, as visual only, the collision will be same. So this is the link, and similarly we have to create a joint for this link. So we'll also create a virtual link which is called the base footprint link. So this is the base footprint link, which is a virtual link, and we will close this link here only. We will start creating the joint. So we will do joint full. We will give the joint name as base joint, and type will be fixed. It is a fixed joint. And origin, right now we will keep the origin as 0 only, and parent link will be our base footprint, and child link will be our base link. Okay, and axis, since it is a fixed joint, we do not need any axis, and also we don't need all these things, lower and upper limits. So this is our joint, and now we can try visualizing this, whatever we have done till now, using RViz. So as you can see that this base link has been imported successfully, and as it was, so we have not changed anything in the visual. As it was, in whichever position it was, it is exactly in the same position as it was in Fusion 360. So now, but if you see in the TF, and if you see in the frames or enabled, I'll switch off, and base footprint is here, but the base link should be here, somewhere here, but the base link is also at the bottom only. So this thing we have to do by manipulating the joints. So what I'll do is I'll place this joint 88 mm above the base footprint, and since I have made the joint 88 mm above, I'll bring the visual minus 88 mm down. This is the only thing you have to do. Whatever value you put in the joint, same value you put in the visual and collision tag, but with opposite sign. So once again I'll build the workspace, but this time I'll do symlink install as well. So every time by doing this, I don't have to build the workspace. Whatever changes I do will be reflected automatically on saving. So here I built the workspace. Now I'll just do again source the workspace and I'll launch it. So now you can see that our base link is here, base footprint is here, and the base link is exactly in middle of the chassis. Doing the similar process I'll do for both the wheels. So I'll just copy this and I'll paste it here. Once again, first we'll change the right wheel joint. So I'll put the values, whatever value I had. So I had 170 mm, which is 0.17 meter, and I have minus 223.50, which is again minus 0.223 and in Z I have 59.50. 59.50. Okay, so this was my joint position. RPY, there is nothing because there is no change in the orientation, there is only change in position. And what I'll do is I'll just paste the negative of this here. So I have pasted these values and I'll just put the opposite sign here. These are the same values which are of the joint, just changing the sign here for the visual tag to adjust. Control C, and I'll paste it in the collision as well. Okay, so this is for the right wheel, and we will do the same for the left wheel. Just so I hope you get what I have done here. We have simply noted the joint values in the previous video. I have written the same joint values which was shown in Fusion 360 here, and then what I did is just wrote the opposite for the visual. This is positive, this is negative, negative, positive, negative, this is positive, this is negative. Same thing I did for all the things to adjust that. So this is how you create the URDF manually. It is a bit tedious, but it works. Okay, so the issue is that since we are using continuous and we have not given the axis about which it should rotate, so this is the axis, it should rotate about the y-axis. That's why it was not rotating. For a fixed joint, we don't need to give the axis, but for a movable joint, we need to specify the axis. Now once again, we will do Control C, try to launch it once again. The wheels are working properly. These wheels are working properly. Yeah. So here we have imported the wheels. Now quickly we'll import the camera and LiDAR and caster wheels using the same. So this is the entire URDF of our robot which we wrote from scratch. These are the materials, and this is the final URDF.jacro file. And we have imported the 3D model in RViz, in ROS, and visualizing it via RViz. Let's see if this thing is moving. It's working. It's working. Now in next tutorials we will learn how to simulate this in Gazebo. See you in the next video. Till then, take care. This was Utkarsh signing off.